Welcome all. Have you ever thought what happens when you power on a microcontroller? Let's take a closer look on how a microcontroller wakes up and gets to work. Welcome to another video in this series where we learn everything about microcontroller and embedded system. This is CocoWall. We innovate, educate and boost tomorrow. We look upon what is a reset sequence and different types of resets. Understanding reset sequence is crucial for debugging low power applications and ensuring system reliability. Specifically, we will see the sequence with STM32F407 based controllers. This can be applied any controllers, for sure ARM based. To get a feel, we will see how these concepts can be applied to Texas Tiva C series controllers. We will use real-world analogies as much as possible to make it relatable. So, let's start. So, what is a reset sequence? A reset sequence initializes the microcontroller, bringing it to a known state before executing the code. It is similar to waking up from sleep. Your body resets, regains awareness, and gets ready for the day ahead. Just like when you wake up, your brain clears out drowsiness, clearing registers, refresh memory, stack initialization, and process pending tasks before you get out of the bed. When it comes to controller, it begins executing instructions. Types of reset. In ST, we can classify the resets as three types: system reset, power reset, backup domain reset. A system reset resets all registers to their reset value unless specified. How can we do a reset? When one of the following event occurs, system reset happens. Low level on the NRST pin, it's also called external reset. Watchdog expiry, soft reset, low power management reset. NRST pin is an external pin in the controller. By making this pin low, we can trigger a system reset. In case of watchdog expiry, the end of count condition of watchdog can trigger a system reset. It is like when we sleep night, we keep alarm to wake up on time and we prevent missing work or school. Next, software reset. It is triggered by setting system reset request bit in Cortex M4 reset control register. Low power management reset is generated when entering standby mode and stop mode by enabling corresponding bits in the register. Low power management of a controller we will see in detail later in this playlist. Right now, this is also one of the reset options for system reset. Now, this is a simplified diagram of a reset circuit. Here you can see NRST pin and the other resets. The reason for reset can be identified from RCC clock control and status register by seeing these status flags. Power reset sets all registers to their reset value except backup domain. Power on reset happens mainly when this event occurs: a power on or brown out condition. When exiting the standby mode also. Backup domain reset. This reset sets all RTC registers, the RCC BDCR register and the BRE bit of the power CSR register to their reset values. This reset can be triggered by setting BDRST backup domain reset bit in RCC backup domain control register. Also VDD or VPAT power on if both supplies have previously been powered off. When it comes to TI, still we can see most of the resets are same. TI provides a beautiful table which explains the reset sources and its effect on controller. So it is advisable to go to your controller datasheet and understand the resets very well. Now let us see the reset sequence in STM32F407. The first step is trigger for a reset. If it is a power on reset, when power is applied. Second step is system clock initialization. At this step, controller ensures a stable clock source for core. How it is done, we will discuss separately. It is a separate topic. For the time being, let us understand a stable clock is ensured. Third step is boot mode determination. So, by default, ARM controller starts booting from address 0. But our flash memory sits in 0x08000000. If our boot mode is selected as X0, that means boot 0 pin is grounded, then always main flash memory is selected as the boot space. The address 0x08000000, that means the flash memory starting address will be aliased to the 0th address. Similarly, consecutive address also. This is how the boot configuration ensures the booting mode is from the selected one. Ignore the word boot for the time being and just understand execution will start from this memory address. Similarly, if boot mode is 01, then the booting will be from system memory. This will be aliasing to the 0th address. Similarly for embedded SRAM also. If you want to know about the various memory regions and architecture of ARM better way, please refer this video and then continue. Next step is vector table load. So what is a vector table? It is a table stored in memory that holds addresses of exceptions and interrupt handlers. The first entry in this table is initial stack pointer value. The second entry is reset handler, which address of a reset handler which executes startup script. This will be loaded in the intended memory address. In case of ST, by default it is loaded from main flash memory base address, that means 0x08000000. It can be relocated to other regions also by configuring vector table offset register. Now stack point initialization is next step. We saw that 0x08000000 address contains main stack pointer value, and this region is mapped or mapped to 0th memory region by memory aliasing technique. So the address mentioned in this location is copied to MSB register. Next step is execution of reset handler on next address, that means 0x08000004. The address of reset handler will be available. This will be copied to PC, program counter next. How a CPU executes code? It will fetch the instruction from address located at PC register. So now reset handler start execution. You can see reset handler of ST here. Here, first execution is system init. It is definition will be available here. This initialize variables and memory. Next, main function starts executing. This holds our next two steps in the reset sequence. Now execution comes in main function. User can write his own code. Now when it comes to Texas Tiva C series controllers, the sequence is exactly the same. The vendor specific difference will be only in the memory addresses and how the boot mode is designed. Here we can see flash memory starts at 0th address, so no memory aliasing technique is needed in this case. And also it has a ROM memory where TI specific bootloader is located. It's called Tiva wire. So as per the boot configuration register, this boot configuration register is designed by this GPIO pins. So as per this boot configuration register, the boot space will be decided. So the sequence are same, only the addresses where memory is located and boot configuration options only vary from controllers to controllers. So what we see is when powered up, how a controller starts executing its first instruction. Stay tuned for next video on Mastering Microcontrollers playlist series. Don't forget to subscribe and press the bell icon. Thank you so much.